In this lecture, I'm going to introduce a new inference rule, the rule of reductio ad absurdum. This rule is meant to allow us to replicate what in mathematics is sometimes called an indirect proof, or in philosophy, what is sometimes called an argument by way of reductio ad absurdum. In order to introduce this rule, let me talk a little bit about what an argument by way of reductio ad absurdum consists in. So here's the strategy behind such an argument. The strategy consists in executing 3 steps. In the first step, one assumes the negation of what one is trying to show. Now, this might seem a little odd to you. If I want to establish a certain conclusion, why would I start off by assuming its negation? Well, the reason one does that is in order to complete step 2. After assuming the negation of what you are trying to show, you then show that the negation of what you're trying to show implies a contradiction, either by itself or in conjunction with your premises. Okay, so you've assumed the negation of what you're trying to show. Then you've showed that the negation of what you're trying to show implies a contradiction. Well, since contradictions can't be true, then it must be the case that what you assumed on step 1 isn't true. So this entitles you to conclude that the negation of what you assumed in step 1 is true. But the negation of what you assumed in step 1 is the negation of what you are trying to show. So by showing that the negation of what you assumed in step 1 is true, you have showed that what you are attempting to show is true. Okay, maybe this seems a little bit abstract, so let me give you an example, a fairly simple example. Suppose one of my children came to me and they asked me if the numbers went on forever. And suppose I wanted to reason with them or convince them that it is in fact true that the numbers go on forever. That is, that the integers go on forever. Of course, they would just ask me about numbers. Here's an argument that I might give them in order to help them see that it is in fact the case that the numbers go on forever. I might say something like this. Well, let's assume that there is in fact, or let's assume that the numbers don't go on forever. Let's assume that there is in fact a biggest number. Okay, now suppose there's a biggest number. Well, if there's a biggest number, then there is also a number that is one more than it, because every number is such that there is a number that's one greater than it. So if there's a biggest number, there's also a number that's bigger than the biggest number. So then what we were assuming is the biggest number turns out not to be the biggest number after all. Or another way to put it, our assumption implies that the biggest number both is and is not the biggest number. But that's a contradiction. That's absurd. That can't be true. So our original assumption must have been false. It must not be the case that there is a biggest number, so it must be the case that the numbers go on forever. That's an argument that I might give my children. It's a fairly simple argument. And what it is it is an argument by way of reductio ad absurdum. And this kind of argument strategy is used in mathematics and philosophy all the time. So we want to add a rule to our system that allows us to replicate that argument strategy. So here is a statement of that rule. Whenever one has a conditional of the form if A, then B and not B on one line, one is permitted to write down the negation of the sentence corresponding to A on a new line. Alright, so what's the justification for this rule? Well, the justification is just this. Since contradictions cannot be true, the rule is self-evidently valid. If you can show that something implies a contradiction, you are entitled to conclude that it is not true. Okay, now an important note here. My way of formulating this rule is different than the way in which your textbook formulates it, and I want you to use this rule instead of the rule your textbook gives. As was the case with disjunction elimination, my reason for modifying this rule is to preserve conditional proof as the sole means of eliminating assumptions. And the way I've stated this rule allows us to do this. The way that your book has stated this rule does not. So you are to do things the way that I am telling you to do them in this lecture, not the way that your book tells you to do them. Okay, now that we have the rule on the table, let's go ahead and look at an example of the rule applied. So here's a fairly simple example. So here's our argument. If P then Q, if P then not Q, therefore not P. So let's go ahead and prove this sequent. Of course, we begin, as always, by writing down our premises. Okay, now that we've written down our premises, we keep in mind our goal, which is to prove not P. But it's not clear exactly what we should do to proceed at this point. There's not much, it would seem, that we can do. Okay, when one is stuck like this, when one has exhausted one's other rules of thumb and it is not clear how to proceed, a good rule of thumb is to attempt a proof by way of reductio ad absurdum. So a good rule of thumb is to attempt to assume the negation of what you're trying to prove, or something equivalent to the negation of what you're trying to prove, and then attempt to derive a contradiction. So that's what I'm going to do. I'm going to assume the negation of what I'm trying to prove on line 3. Well, actually, that's not quite right, because technically the negation of what I'm trying to prove, namely not P, would be not P. And instead of assuming not P on line 3, I've simply assumed P. But that's equivalent to the negation of not P, and this saves me having to go through a double negation step. I could have assumed not P on line 3 and then proceeded on with my proof, and that would have also been correct. But so I don't have to bother with a double negation step, I'm just going to assume P. Okay, now that I've assumed the negation of what I'm trying to prove, or at least something equivalent to the negation of what I'm trying to prove, I now make it my goal to attempt to derive a contradiction. Now, a contradiction, you should keep in mind, is a sentence of the form be and not be. That is, a contradiction is a conjunction where you have one sentence conjoined with its negation. So I want to derive a sentence of that form. And it's not entirely clear what I can do at this point, but one thing I do note is that I have these two conditionals on lines 1 and 2, and I have their antecedent on line 3, so that puts me in a position to apply modus ponens. So I'm going to go ahead and do that. I apply modus ponens to lines 1 and 3, that gives me Q. I apply it again to lines 2 and 3, that gives me not Q. Now I see on lines 4 and 5 I have the materials I need to derive a contradiction, because I have Q on line 4 and I have the negation of Q on line 5. So now if I can put those together via conjunction introduction, and that gives me a contradiction. It gives me a sentence of the form be and not be. In this case, that sentence is Q and not Q. Okay, now that I have my contradiction, I've accomplished one of my subsidiary goals, which was to derive a contradiction from the assumption that I made for the purpose of reductio. So now that I've done that, I'm going to go ahead and discharge that assumption. That is, I'm going to discharge the assumption that I made on line 3. That gives me the conditional if P, then Q and not Q. So now I have a conditional with a contradiction as its consequent, and via the rule of reductio ad absurdum, that entitles me to infer the negation of that conditional. So I've done that. I've affirmed that entitles me to affirm the negation of the antecedent of that conditional. And I've done that. I've inferred not P on line 8 via the rule of reductio ad absurdum. And that is what I wanted to prove, so I've now completed this proof. Okay, we're going to look at some further examples in the next part of this lecture, but for ease of recording I have broken up this lecture into 2 parts.